to take seminar on the topic bipolar junction transistor. First of all, a bipolar junction transistor is constructed by 3-dot semiconductor separated by 2 p-n junctions. The three regions are called the emitter, base and collector. One type consists of 2 n regions separated by p region, and the other type consists of 2 p regions separated by an n region. The p-n junction joining the base region and the emitter region is called the base emitter junction, and the p-n junction joining the base region and the collector region is called the base collector junction. That is, this is an example for a p-n junction, which is this region is the base collector junction and this region is the base emitter junction. There are two types of transistor, NPN transistor and PNP transistor. In the NPN transistor, it is a transistor which consists of N region separated by a P region. Okay. And the collector, this is the collector and it's the base and it's the emitter. The collector is moderately doped and the base is lightly doped and the emitter is highly doped. And this is a symbol of a PNP transistor. And this is the symbol of an PNP transistor. Sorry, this is an example for NPN transistor. Next, we can discuss about the basic transistor operation. The transistor operate properly as an amplifier when this transistor is connected to external DC voltage, and then it works as an amplifier. Now we are going to connect the transistor to external voltage sources. Here we are considering a PN junction, PN junction transistor. So we are connecting the base to a resistor and then to a DC voltage source. Then it's connected to earth, and here also we connect a voltage source, and then it's connected to insert. Okay. Now this is this resistor is an active region because its base emitter junction is forward biased. This is an active region because it's forward biased. What's forward biased is the base emitter junction is forward biased and the base collector region is reverse biased. That's the emitter is forward biased and the collector is reverse biased. Okay. And at this condition, VB is greater than VB. That's the voltage at the base is greater than the voltage of the emitter, and VC is greater than, voltage of the collector is greater than VB. At this condition, the transistor is in the active region. And the next biasing condition is when it is in the cutoff region. When will this transistor will be in cutoff region? That's when both the sources are reverse biased. That is, when both the sources are reverse biased, VBE is less than VE. That is, here V is greater than VB and VC is greater than VB. At this condition, that is when both the emitter and the collector is reverse biased, the junctions are reverse biased, the transistor is in cutoff region. That is, it works as a switch, and when collector is reverse biased and the emitter is forward biased, it is in the amplification condition. That is, it works as an amplifier. At this condition, it is in cutoff region. Okay. The next condition is the saturation condition. That is, both the emitter and collector junctions are forward biased. At this condition, when both these are forward biased, VB is greater than VE and it is greater than VB is greater than VE. At this condition, the transistor is at saturation region. Now when we are considering the case at which the transistor is in the active region, the forward bias from the base to the emitter narrows the BE depletion region. That is, when we forward bias this, the base region narrows. It narrows, and the reverse at the condition where which we reverse bias this, the collector widens. The collector widens the depletion region. Okay, and the heavily doped intact emitter region is giving the conduction band electrons that easily diffuse through the forward biased VE junction into the p-type base region where they have the minority charge carriers, just as in the forward biased diode. The base region is lightly doped and very thin, so that there is limited number of holes. Okay, it's lightly doped and there is only limited number of holes, and only a small percentage of electrons flowing to the VE junction can combine with the available holes in this base. So there is only small current, and these relatively few electrons flow out of the base and lead as valence electrons, forming a small base electron current. Okay, that's all what we are discussing here. And next we are going to discuss about the transistor currents. We know that this is the base region. Okay, so this is the collector. This is the base current IB. This is the base current IB, and this is the base current. This is the emitter current IE, and this is the collector current IC. This is the base current IB, emitter current IE, and the base current IC. Okay. Now we can see that in this figure, IE is equal to IB plus IC. We can, when we look at this figure, we can know that IE is equal to IB plus IC. That is, when actually we know that IB is very small. So in such condition we can approximate that, we can say that IE is approximately equal to IC. Okay, this is the transistor currents. This is what we can see about the transistor current. So this is all what we discussed today. Thank you.